All right, good morning, everyone. So, just one announcement to start off with. The exam number 4 example solutions are now posted. I posted those this morning, so you can go through those if you've already started working on the problems. Check how you're doing. So first thing we're going to start off with today is this idea of eddy currents. So what's an eddy current? So I'm going to show you a couple videos here about what eddy currents are. So in this first video, you'll recognize this handsome person, that is me. Okay, so what I'm going to be doing here is I'm going to take neodymium magnets. Does anybody know what neodymium magnets are? They are ridiculously strong natural magnets. Okay, so these things are very powerful magnets. What I'm going to do here is I'm going to drop them down through the center of 2 different objects. The first one's going to be a PVC pipe, and then the second one is going to be a copper pipe. Now, copper is a paramagnetic material, which means that it is not a ferromagnetic material, which means that it's not a permanent magnet. It has no magnetic properties to it. Okay? So all we're going to do here is watch the difference between me taking the neodymium magnets, dropping them down through the center of the PVC, which is what I have first, and then with the copper. So I'll show you this, and then I'll show you another video made by another handsome person. So that falls out. Hopefully you can kind of see it fall out to the bottom. I'll back that up just a second. So when I drop it down, watch here, you can see it drop out basically immediately. It's falling at the rate of G. Okay? I'm just simply dropping it. So I have copper, that's our metal copper. It's non-magnetic. I'm going to drop it in. And it takes a whole bunch more time for that to actually fall through. We'll talk about why that is in a second. Let's show another video. So now what this guy is going to be doing is he has also a piece of copper. So here's the copper on here, and then he has a piece of wood, which then has a tap running through it. And he's simply going to cause this thing to harmonically oscillate as a pendulum.
You can see it moves fairly freely and continues to swing for a reasonably length of time. But what if I now actually start it to swing and then bring my magnet really close to it without touching it? As you can see, the piece of metal slows down reasonably quickly.
So the reason for both of these things is what we call eddy currents. So what an eddy current is it is a response to the fact that I again have a time-dependent changing magnetic field, which means I have a time-dependent flux. So basically what an eddy current is then, has to be in a metal. It can't be in something like PVC because PVC is plastic. It's an insulator which has tightly bound electrons. So it has to be done in a metal where the electrons are actually free to move. So what happens is as this thing is moving, the magnet is moving inside of this copper pipe, for example. What it's doing is it's creating currents that move around inside of the copper. These are what are called eddy currents. So the current is moving around in circles inside of the copper, which then creates magnetic forces acting onto our magnet. So let's say here's my copper rod or my copper pipe. Inside of here, I'm going to have my magnet. So here, let's say this is the north side, this is the south side. So my magnetic field points down in this direction. So what's happening then is what? For a ring around here, the magnetic flux is increasing, which means I have to induce a magnetic field inside of this ring across here in the opposite direction, which basically means that I'm going to have current flowing down here in this direction to then induce an induced magnetic field in the opposite direction. So what's happening here is I'm creating a magnet here due to the fact that current is flowing inside of the ring here, which then creates a magnet pointing in this direction, which means I get a magnetic repulsion between the two. But for a ring up here, what happens then is the magnetic flux is decreasing, so I have to induce a magnetic field in the same direction as the external magnetic field. So what happens up here now is I'm going to create a magnetic field pointing in this direction. This is going to be my V induced, which means my current then has to be flowing in the opposite direction. So now my current is flowing this way, which now creates a magnetic attraction between the North Pole here and the South Pole here. So these are what are called eddy currents. So as the magnetic flux is changing, the system again wants to keep it at a constant magnetic field. So current then is going to flow through the metal object, creating temporary magnets as this thing is falling through. So what I'm getting here is a magnetic repulsion here, so I'm getting a magnetic force pushing upward. But then here I'm getting a magnetic attraction, also creating a magnetic force pulling it upward. So this is the reason why the magnet was falling at a very slow rate, because now it's not accelerating at the rate of g anymore, it's just kind of almost floating, like levitating. In the other case, what was happening is the same thing. As the piece of copper is swinging in and out of the magnetic field, it's creating these eddy currents. So what happens in that case is here is my piece of copper. As it's swinging in, say, this direction, what's happening here is, let's say my magnet is here. So on this side, the magnetic flux is getting smaller. On this side, the magnetic flux is getting bigger, which means that this is going to have, again, magnetic forces. We're going to create a magnetic force in this direction and a magnetic force in this direction, causing it to slow down if this thing is swinging in this type of direction. So what happens is, again, as this thing is moving, if the metal is moving in the external magnetic field, it creates little pools of current, where these pools of currents are then moving in opposite directions. So on this side, my current's going to move in this direction. On this side, my current's going to move in this direction. These pools of current are what we call eddy currents. Okay? This is how a metal detector works. So with a metal detector, what you do is as you swing this thing around, what it's doing is it's sending out pulses of magnetic fields. Those magnetic fields then get caught up in metal, create eddy currents, which create magnetic fields inside of the metal, which then creates a residual magnetic field. And what you're looking for is that residual magnetic field when you're using your metal detector. Also, if you walk into a building that has a metal detector, that's also what they're doing. On one side, they send a pulse. That pulse then goes through you, goes into something like your keys. Even though my keys are non-magnetic, they're still metal, which creates eddy currents, which creates a magnetic field inside of my keys. So when that pulse goes from one side to the other side, there's a residual magnetic field for my keys, which then takes more time for it to go to the other side of the metal detector, which causes the metal detector to go off and say, hey, there's now a time lag between the original pulse which was sent and now a new pulse which I'm gaining because of the residual magnetic fields because of these eddy currents. This is how a magnetic field or a metal detector actually works. So all of this is done by these eddy currents. So again, anytime I have a time-changing magnetic flux that creates current inside, which then creates residual magnetic fields, which creates either repulsive or attractive magnetic fields. So, any of you guys heard about these levitating trains that they have in Japan? This is how you stop a levitating train. So when you want it to stop, you put magnets. As it moves through the magnets, creates these eddy currents, causes it to slow down. It's called magnetic braking. So all of this is done by eddy currents, all based off of Faraday's law. Okay, so these are eddy currents. Great. So next thing I want to talk about is what is actually the relationship between the electric field and the magnetic field. To do that, I'm going to show you another video. And I'll explain what he's doing here. He's also going to explain it, but I'll explain it first. So basically what he's going to do is he's going to take a solenoid here. Here's a solenoid, which means that he's going to have a magnetic field going only along the axis of the solenoid, which means the magnetic field is concentrated to where the solenoid is. So all the magnetic field is only here. Now, you can kind of see in the video, he has a loop of wire here, which is outside of where the magnetic field is. Now he's going to do exactly what you guys did in lab, which is close the switch. And what you guys saw in lab is when you close the switch, you created a time-dependent magnetic field because it's a solenoid. We'll talk about what this happens in a second. But it takes time for the current to build up inside here, which means it takes time for the magnetic field to build up. And what's going to happen then is he's going to show is in this loop here, he's actually going to create a current. Even though the loop here is nowhere near inside of the external magnetic field. Right? So he's going to create a time-dependent magnetic field here, but that's going to create a current inside of the loop, which is outside of the external magnetic field. So I'll have him demonstrate that.
Turn the current on, and only while the current is changing will there be a changing magnetic flux. Only during that portion will you see a current flow. 3, 2, 1, 0. I will break the current. 3, 2, 1, 0. When do you go to that direction?
Now, mind you, the thing here is that the loop is not in the external magnetic field. which means that the current is moving not because of a magnetic response. These charged particles inside of this loop, i.e. the electrons, cannot feel a force due to the magnetic field. They're not in the magnetic field. This is kind of weird. Now he's going to do it again. This time he's going to make the loop smaller. Got to change the configuration of the loop.
If I change the size of the loop, I'm making it now different. Much smaller makes no difference for reasons that I explained to you, because the magnetic flux is not determined in this case by the size of my loop, but is determined by the solenoid. So if I do it again now, it's a very different shape of the loop. Let me zero this again. 3, 2, 1, 0. 3, 2, 1, 0. No change. Almost.
So, again, what he's basically saying here is, again, the size of the loop doesn't matter because all of the magnetic field is concentrated here inside of the solenoid itself. So the response that he's getting inside of the loop, whether it's this size or this size or this size or much bigger, stays the same because it was never inside of the external magnetic field to begin with. All the magnetic field is simply concentrated here. So he's not changing anything about the area of the magnetic field, only the area of the loop, but the response is independent of the size of the loop. I'll talk about this in a second. So what's really weird, what's kind of really bizarre about this is we've seen EMFs created by the fact that an object was moving in an external magnetic field. And what that would get us to think in our brains is that what's actually happening is it's a magnetic response. I'm creating the currents due to the fact that I have a magnetic response, i.e. a magnetic force, which is causing the current to move. What this is showing is that's actually not true, because the loop was never inside of the magnetic field to begin with, which means I'm creating a current not because of a magnetic response, but because of an electric response. So what's actually happening is they're actually feeling a force due to an electric field, which is being generated inside of the loop, not because of a magnetic response. This is actually very weird. And what's more weird about it, which we're going to talk in a second, is that this electric field that's created is not a conservative force. Unlike the electric field that we talked about before, which we had a potential for because it was a conservative force. This is a different type of electric field, but it's still electric field nonetheless. So let's talk about this. So this is the relationship between the electric field and the magnetic field. So electric field and magnetic field relationship. So good. So let's think about this. So let's think about Faraday's law. So what Faraday's law says is that what? The EMF, which is generated, is equal to minus the number of loops times the time rate of change of the magnetic flux, which is then equal to minus n times the time rate of change of the integral of the electric field dotted by the differential area. Now, okay, let's think about what's happening here. So what's happening here is, again, here is his solenoid. Okay? So what's happening here is he's running a current through a solenoid. Let's say my current is going in this direction, but this is a time-dependent current. That time-dependent current then creates a magnetic field. So in this case, my current's running in this direction, so my magnetic field is going to point in this direction. So he's creating then a time-dependent magnetic field in this direction. Okay? Now, around this, he then has his loop of wire. So here's my loop of wire. And what's going to happen then is he's going to create a current inside of this loop of wire, which actually ends up going in the opposite direction. Of course, this is going to depend on if this thing is increasing with time or decreasing with time, but let's just say it goes in the opposite direction for now. So good. So let's think about the flux. So what we know is this is a solenoid. So we know the magnetic field of the solenoid is equal to mu naught n times I, which means this thing is spatially constant. So this is not equal to a position-dependent magnetic field, which means our magnetic flux then is going to be equal to just the magnetic field times the area. So if I put these together, this is then going to be what? Mu naught n times I times, I'm just going to leave this in terms of the area. for now. So what this says then is that the rate of change of this magnetic flux, the only thing that's changing here is the current, right? The current is actually what's changing with time. So as I start running this through here, this solenoid has a time-dependent current. We're going to talk about that in just a minute. So that means this is going to be equal to mu naught n times the area times the time rate of change of the current. So let's stick this into Faraday's law. Let's say there's only one loop, make our lives a little bit easier. So this says that Faraday's law says that the EMF then is equal to minus the time rate of change of the magnetic flux, which for us then is equal to minus mu naught n times the area times the time rate of change of the current. So that's then the right-hand side. So what about then the left-hand side? So the left-hand side, this is then the change in potential. So basically what's happening here is I'm creating a change of potential through this loop, where if I measure it at this point here, let's call this point A, and I come back to the point A, then my change of potential going from A to A is not equal to 0, but it's actually equal to the EMF. So what this means then is if I do my closed loop integral around this guy, and if I go from A to A, if I had a conservative force, i.e. a conservative electric field, this change of potential should be equal to 0. Well, what's happening here is if I start at A, I go around my loop and I come back to A, my change of potential is not equal to 0, but I've actually increased by an amount of the EMF. So what that means is, so let's go back to our potential. So remember that what we said before was that the change of potential was equal to minus the integral from A to B of the electric field dotted by the differential length, which means here that our EMF then is equal to minus the integral of the electric field dotted by the differential length over a closed loop. So if I use this now into the left-hand side here, I'm going to leave this as a positive, make that as positive for now. I'm going to make this as the closed loop integral of the electric field dotted by the differential length. This, actually if I put it up here, closed loop integral E dot dl, this is actually Faraday's law. So what Faraday's law actually says is that what we're really doing is we're actually inducing an electric field inside of the loop. So if I have a time-changing magnetic field, a time-changing magnetic field then creates a time-dependent electric field. That's what this thing is saying. Now, moreover, what this thing says then is the direction at which the electric field is induced would be in the direction of the induced current, which would be opposite of the change of the magnetic flux. So the magnetic change flux is getting bigger than the electric field is induced in the opposite direction to make this thing remain constant. Now, what's really weird about this electric field is, first of all, it's non-conservative because if I do a closed loop integral, this thing should be equal to 0 if it was conservative, but in this case, it's non-conservative because it's not equal to 0. The second thing is, since this is a closed loop integral, what this means is that my electric field actually has to form closed circles, not straight lines like we've seen before. So this electric field is really, really bizarre. So this electric field is first not a conservative electric field. And this thing forms closed circles. So if I go back to my picture, what's really happening then is I'm actually creating an electric field inside of my loop, which is then pointing in this direction, as long as, in this case, my magnetic field is increasing. If my magnetic field is decreasing, the induced current and the induced electric field will actually be in the opposite direction. So, what's really happening in Faraday's law is the response of the currents moving inside of the rod or wire or whatever it is not a magnetic response, but is actually an electric response. it is creating an electric field, which is different from the electric field that we saw before, in the fact that this electric field is not a conservative electric field, and it forms closed loops just like the magnetic field, opposite to the electric field that we saw before. So this is actually our relationship then between the magnetic field and the electric field. The relationship is that the closed loop integral of the electric field dotted by the differential length then is equal to minus n times the time rate of change of the integral of the electric field, or sorry, magnetic field dotted by the differential area. So this is actually Faraday's law. Faraday's law then tells us that an induced electric field comes from a time-dependent magnetic field. So this says is that a time-dependent magnetic field creates then an electric field. But it creates it in such a way that it's negative. It's opposite to the change. Completely opposite to the change. Put this in context. Your drunk friend wants to jump off the bridge. You are the magnetic field that says, yeah, I might not want to do that. And this is what Faraday's law does. What Faraday's law is it pulls it back. It does it in the opposite direction. So the fact that this guy wants to do something, this guy is saying, well, we might not want to do that. Let's think about this. I know we're drunk, but that's fine. We don't want to die. Now, this will be different from something that we're going to see after the exam, which is we're going to do a modification to Ampere's law, which then says that actually a time-changing electric field also induces a magnetic field. But it induces it in such a way that it makes it get bigger. That's your other drunk friend that says, hell yeah, let's jump off the bridge. Okay? Got to have two friends. One's got to pull you back, the other one's got to push you forward. Need both of them. And it's actually the interplay between these two things which gives us light. And we'll talk about that. So this is where light actually comes from. But this is what Faraday's law actually says. So what Faraday's law actually says is that what's really happening is it's an electric response, not a magnetic response. And what you're actually doing is you're creating an electric field which forms closed loops in the direction in which the current is going to go, which creates an external magnetic field, or actually creates an induced magnetic field, i.e. Faraday's law. Okay, so let's do an example of this. I know we got most of the pieces here, but let's do an actual example. So this says we have a magnetic field between the poles of an electromagnet is nearly uniform at any instance over a circular area of radius r0. So let's start drawing a picture. So all this means is, let's say this is my circular plate. This has a radius of little r0. And what we're saying here is that we have a magnetic field anywhere on the interior, which is say pointing in this direction, and this thing is spatially constant. So here, B is not a function of position. So what this says then is the current in the windings of the electromagnet is increasing over time so that the magnetic field changes in time at a rate of dB dt at each individual point. Okay. So then I want to know, beyond the circle, we assume that the magnetic field is equal to 0. So what we're saying here is that the magnetic field out here is equal to 0, so anywhere outside of here. And what's happening is that the magnetic field here is increasing over time, and it's increasing on a time at the rate of dB dt, which is equal to a constant. So it wants us then to determine the electric field at any point P at distance r from the center of the circular plates there due to the change in the magnetic field. Okay. So basically what we want to do is determine what is the electric field and how is that guy actually changing. So the way that we're going to determine the electric field, let's think about that guy first, is again to use our right-hand rule. Okay. So again, the first thing we need to know is, since here, anywhere in this region, I have a magnetic flux. That magnetic flux is increasing, and the magnetic field is increasing because it's pointing in this direction. It's increasing because we're told. Now, what that means then is what? Since the flux is getting bigger, Faraday's law then says, or actually Lenz's law says, we have to create an induced magnetic field, which is going to point in the opposite direction of this guy. Okay? So what this means then is we're going to induce a magnetic field in the opposite direction because the flux is getting bigger. Now, right-hand rule number 3 says, for my thumb to point in the direction of the induced magnetic field, my fingers have to curl around in the direction of the induced current, but my fingers curl around in the direction of the induced current, which is in the same direction as the electric field. Okay? So what's happening here is I'm actually creating an electric field, which is circular, pointing in this direction. So let's say this is my distance r. So what I want to know is, what is the magnitude of the electric field anywhere inside of the plates? But simultaneously, what's the magnitude of the electric field anywhere outside of the plates as well? Because we know we have to make an electric field outside there, even though it's outside of the region where the magnetic flux is actually changing. So let's call this distance also r. So good, so let's do that. So let's apply our new results. So now we know is that we have the integral of E dot dl, which is a closed loop integral, is equal to minus, we're going to say there's one loop, so that's going to be 1, times the time rate of change of the magnetic field, integral B dot dl. Okay. Now, in this case, since we're looking for the magnitude of the electric field, I'm just going to look at the magnitude of all this. I'm going to make that guy constant since it's just the magnitude. Remember, the negative just means the direction. So in this case, since we're looking for the magnitude, so we want the magnitude. So let's deal with the right-hand side first. So here, we're told that the magnetic field is roughly constant over the entire area, which means that the magnetic field is only time-dependent. It is not position-dependent. Which means that, in this case, the magnetic field is going to come outside of the integral. I'm going to have the integral of dA, which is simply A. So the right-hand side then is going to be equal to the time rate of change of the magnetic field times the area. Okay? So in this case, this is going to be equal to the area times the time rate of change of the magnetic field. So that's going to be the right-hand side. For the left-hand side, this thing just looks like Ampere's law, so we're going to do exactly the same thing we do in Ampere's law. So what we're going to do is we're going to draw a loop which mimics what the electric field looks like. So what this means is, going back to our picture, for this one, all I'm going to do is I'm going to draw a DL, or a loop, which follows exactly the path of the electric field. So in this region, I'm going to draw DL this way, and now here I'm just going to draw DL this way. So this is my DL. Now again, the reason we want to do that is because in this case, E points in exactly the same direction as DL, which means the dot product between the two becomes a cosine of 0, which is simply 1. So that means the left-hand side just becomes the closed loop integral of the electric field times the differential length. But what can you tell me about the magnitude of DL everywhere then along, or the magnitude of E everywhere along DL? Is it constant or is it non-constant? It's constant, right? So everywhere along the circle, the electric field is equal to a constant, DL. So as far as DL is concerned, E is simply a constant, which means that guy comes outside of the integral. So same thing we did with Gauss's law before. So this is the same thing then as the integral DL times the electric field. But the integral of DL is simply the length of this DL that I drew, which means that this is simply a circle. So this becomes E times 2 pi r is equal to A dB dt. So from here, what this says then is that the magnitude of the electric field is then going to be what? The area divided by 2 pi r times dB dt. Now, the only question we have remaining here is, well, what is A? What is this area? So the answer to this area is going to depend on, say, part A, when r is greater than r0, and then part B, when r is less than r0. So let's think about A for each one of these regions. So what we want to care about is, let's go back to our picture. What area do we care about? So in this problem, let's say I'm looking at here where r is greater than r0. So I'm looking at this green line out here. What area do I care about? Do I care about the entire area, so this pi little r squared, or do I care about only the area here, which is then pi r0 squared? So as far as the area here is concerned, what area am I talking about? So where did this area actually come from? Well, the area came from the magnetic flux. So let's think about the magnetic flux. So if I go back to here, even though I have this area here and this area here, where is the magnetic flux confined to in this problem? Where is my flux? Where is it confined to? i.e., where is the magnetic field? So is the magnetic field stretching all the way out to the big green, or is it concentrated to someplace else? It's concentrated to someplace else. Where is it? Just the size of the plates. So when I'm on the exterior, I don't want to care about the area all the way up to here because there is no magnetic field in all of that area. The magnetic field is concentrated between the area of the plates, which means as far as the flux is concerned, the flux is only inside of the solenoid, which means it's only confined to this region here. So in this region, when R is greater than R0, the area I care about is only the area of the plates. So for part A, I then have my electric field then is equal to what? Pi R0 squared divided by 2 pi R times then the time rate of change of the magnetic field, which means my electric field then is going to be R0 squared divided by 2R times the time rate of change of the magnetic field. This is part A. When R is greater than R0. What about when R is less than R0? Let's go back to our picture. So here, what's happening here is now I'm talking about the smaller green circle. So here this has a radius of R. Now what area do I care about? Do I care about the area of the small circle, or do I care about the area of the plates? Which area do I care about now? Which one? So again, what I'm looking for is the flux through that circle. So do I care about the area using little r or the area of the plates themselves? Dylan, what do you think? That's up in the gray, yeah. Which one? Let me the small one, right? So here, all I care about is the flux which is passing through this loop. So even though there's flux all the way out to here, I don't care about it because I only care about the flux which is passing through my loop that I'm drawing. So when it comes to part B, my area then is going to be simply pi r squared, which is going to be the r of the loop at which it is I draw. Which means for part B, my electric field then is going to be equal to pi r squared divided by 2 pi r times the time rate of change of the magnetic field. So this is going to cancel with this will cancel with that. So this becomes r divided by 2 times dB dt. So this is my electric field. So again, what Faraday's law is actually saying is what I'm doing is I'm creating electric fields. These electric fields form closed loops, which means they're not conservative electric fields, but they're in such a way as to generate an induced magnetic field, which is opposite to the change. In this case, my magnetic field was increasing over time, which means I had to have a magnetic field induced in the opposite direction to kill off the fact that this guy was increasing. If this was decreasing over time instead, what happened in that case is I'd have to actually induce my magnetic field in the same direction as the external magnetic field to counteract the change of the flux, which means the only thing that's going to be different is my electric field lines would go in the opposite direction. Everything else would stay the same. Right? So instead of having electric field lines which are in a clockwise direction, they would then have to go in the counterclockwise direction if it was decreasing over time instead of increasing. That's the only difference. Okay. Not easy stuff, I know. So, but again, here it's just an electric field. So everything we see here is an electric response, not a magnetic response, but it's a completely new electric field. It is a non-conservative electric field, which forms closed loops as opposed to straight lines. So this is what's actually happening in Faraday's law. We're creating an electric field from a time-dependent magnetic field. And as we'll see after the exam, the opposite is also true. We have a time-changing electric field will also create a magnetic field. So, we're okay? Hopefully. Don't lie to me. Okay. So, next thing we'll talk about is, how do I know that current inside of the solenoid takes time to charge up? How do I know this? Well, this is what's known as inductance. So let's talk about inductance. Now, typically, there are actually two different types of inductance. There's what's known as self-inductance and also what's known as mutual inductance. So let's kind of briefly talk about both of them, and then we're going to concentrate only on self-inductance, not on mutual inductance. But let's talk about it. So what is self-inductance? So self-inductance is, let's say I take a battery and I attach that to an inductor. So here's my inductor, which is also what's known as a solenoid. So I'm going to put a solenoid in here. So what happens? Well, let's say I had a switch. So here's my switch. Draw a switch on here. So let's say at t is equal to 0, I'm going to close my switch. So when I close that switch, what's going to happen then is the battery is going to force current to start moving through the circuits. So t is equal to 0, I'm going to go ahead and close the switch. So current then is going to start moving through the circuit. So what happened? That current then is going to start to encounter onto my loop. Let me draw it on another page. So let's say here's my loops. So what's going to happen then is I'm going to start having current flow through here. Okay? So what's happening here is I'm starting off with 0 current at time is equal to 0, trying to now push through a current of maximum amount of currents, right? Which means that since I have current running in this direction, I'm going to create a magnetic field because we know magnets are created by currents. So I put my thumb in the direction of the current, my fingers curl around in the direction of the magnetic field, which means that what? Here, I'm going to create magnetic field lines which point into the page. So this is going to be true at all of these different loops. But since I went from 0 current up to maximum current, this is now a time-dependent magnetic field, which means that I'm creating a magnetic field from 0 up to a maximum in a short amount of time, which means that I have a flux now inside of each one of these loops. Each one of these loops doesn't want to have a flux, so what it's going to do is it's going to create its own magnetic field in the opposite direction, since this is increasing with time. So I have an increasing current with time. So I'm then going to induce a magnetic field in the opposite direction to counteract that increasing external magnetic field. So what's that going to do? Well, what that's going to do is it's going to force a current to run on the inside of the wire in the opposite direction. So this is our induced current, also known as a back current, which is then going to try to slow down the rate at which this current is flowing. So what'll happen then is I'm going to get a total current running on the inside, I total, which is then equal to the current which is trying to be pushed through it, minus then the amount of this induced current. But simultaneously, as I'm increasing a magnetic field and increasing a current, I'm also generating a potential. I'm creating what's known as a back EMF. So inside of here, I'm also creating an EMF, which is what's called a back EMF. So what's really happening is, this is why it's called self-inductance, is as I'm trying to force current through the solenoid, as it originally had no current running through it, it creates its own current in the opposite direction, trying to cause a lag in the current. So this thing isn't automatically going from 0 current to maximum current. It takes time for this thing to actually build up. So what's happening is this solenoid is influencing itself, causing itself to take more time to actually charge up. Because it's trying to force current in one direction while the battery's trying to push current in the opposite direction, which causes it to take more and more time for this thing to actually charge up. So the system is actually hindering itself. What happens if I have current running through the system, but then I turn off the system? Well, if I turn off the system, I go from maximum current trying to go down to 0 current, which means the flux inside of each one of these is getting smaller, which means I have to induce a magnetic flux in the same direction, or magnetic field in the same direction as this external magnetic field, which means the induced current is actually going to go in the opposite direction, which means it's going to take time for this thing to go from maximum current all the way down to 0. It's not going to happen instantaneously. It's going to take time for this thing to happen. So in that case, the system is actually trying to help itself out by having the current stay constant instead of having it go to 0 directly. This is what we call self-inductance. So self-inductance is when the system is feeding off of itself, either hindering itself or helping itself depending on the situation. This is called self-inductance. So what's mutual inductance? So mutual inductance is if I have, say, 2 of these loops next to each other. So here's one loop here. Here is a second loop, but I have no battery on this side. So in this case, let's say the current is going down. So here I have current going down in this direction. So since current is going down in that direction, over here I'm going to create a magnetic field which is pointing outward. So this will be the magnetic field from loop 1. So if this is loop 1, this is loop 2. So what happened then is, again, if this is increasing with current, this magnetic field will be getting bigger. So loop 2 is going to create its own magnetic field in the opposite direction to try to counteract that change, which then causes an EMF built inside of here. But the EMF in here creates a magnetic field on this side, which also causes the current to build up in the opposite direction here, which means what happens in mutual inductance is I'm actually affecting this one by having this one change. But simultaneously, as this one changes, this is going to force this one to change in a different way as well. These two systems will simultaneously feed off of each other in either a helpful way or a non-helpful way, depending on if the current is increasing or decreasing. This is what's called mutual inductance. So if I take one current here, I can induce a second current in the other one, even though the other one never had a power source. This is exactly what you guys did in lab. So the orange is the induced magnetic field from this loop. It's the response of him. So this is exactly what you guys did in part D of the lab. You were actually playing with mutual inductance. So you had one coil, which had a time-dependent magnetic field, inducing a time-dependent magnetic field inside of the other one, which then induced the current inside of here. You can use this for good things. For example, any of you have a parent or grandparent that has a pacemaker? This is a good way to charge a pacemaker. A pacemaker actually has an inductor on the inside, and what you can do is actually charge up that inductor without having to cut the person back open to put a new battery in every time that the battery of the pacemaker died. So by taking this guy, you can put that person in an external magnetic field, cause that thing to change over time, that induces a magnetic field inside of him, which induces a current, which causes mutual inductance inside of that pacemaker to then charge the pacemaker, with never actually having to cut that person over again. Okay? So this is what's called mutual inductance. This one, as far as mathematically wise, we're not going to play too much with that, but I just want you to be aware of it. It's called mutual inductance when two systems actually feed off of each other. What we want to do is actually concentrate on this guy. So let's look at him. So self-inductance. So what's happening in self-inductance? So what self-inductance says is that the number of loops times the magnetic flux is then equal to L, where L is what's known as the self-inductance or the inductance, times the current. So all this thing is saying is that N, which is N is the number of loops, so the flux through each one of these loops is then creating a current, which in this case is the induced current, times some proportionality factor, which is what's known as the inductance of the inductor. So of the inductor. So it's basically the capacitance of a capacitor. So what this thing says then is what? We saw this, the inductance then is equal to the number of loops times the magnetic flux divided by the current. So this is what we define as self-inductance. Now, what we also know is that the time rate of change, though, of the magnetic flux is equal to the EMF. So if I go back to that expression, this guy equal to L times I, let's take a time derivative of both sides. So what this thing says then is that the number of loops times the time rate of change of the magnetic flux is then equal to the inductance times the time rate of change of the current. But Faraday's law says that the number of loops times the time rate of change of the magnetic flux is equal to negative of the EMF. So what this says then is that the back EMF which is generated, the back EMF, which is generated inside of the coils then is equal to minus the inductance times the time rate of change of the current. So this is what we call back EMF. So what does this mean? So what this means is, if I go back to my inductor, what this means is if I measure the potential difference between a point here and the point here, what happens then is as the current is actually changing with time, I get a potential drop between this point and this point, which means that the potential difference between point B and point A then is negative of the inductance times the time rate of change of the current. So while the current is actually increasing, this thing acts almost exactly like a resistor. It causes a potential drop. So this is what we call reactance. Okay? So what's happening is as current is running through here in a time-dependent fashion, that creates a potential difference between one side to the other side. But once the current reaches then the current which is driving through the system, i.e. that which is dictated by the battery, the time rate of change of the current then goes to 0, which means this thing acts like a regular straight wire, which means that there's no potential drop. Then a potential drop between point B here and point A, in that case then, so delta V, would be equal to 0 when this thing is finally charged up. So this thing actually acts like then a straight wire. Now what happens then is the battery has to do work onto the system to ensure the fact that I'm going to overcome this induced current in the opposite direction to then charge this thing up over time. Which means that this thing actually stores energy, and it stores energy via the work it takes for me to force this current via the battery to overcome the induced current in the opposite direction. Okay with this? So this thing, as we mentioned before, is actually then the magnetic equivalent of a parallel plate capacitor because its function is to store energy. The point of putting an inductor then into a system is that inductors store energy via the work to charge up the current. So how much energy does it then store? Well, what we know is, going back to exam 3, the power delivered by the battery to any electrical circuit is equal to the current times the potential. In this case, this is the power delivered then by the battery to the inductor, where this is going to be our back EMF. So the power then is going to be equal to then, so the current times then the inductance times the time rate of change of the currents. So in this case, this is the power delivered to and the power lost by the inductor itself. Now, remember that power, though, is equal to the time rate of change of energy. So the amount of energy which is stored via the amount of work that the battery is doing to force this amount of power to go through it then is going to be simply the integral of this guy. So what this says then is that the energy is equal to the integral of the differential energy, which is then equal to the integral of the power integrated over time. Okay? Now here, inductance is simply a constant. I'm going to pull that guy out. So this thing is going to be equal to the inductance times the integral of I di dt dt. Well, what happens to those two dt's? They're going to cancel. Okay. So this guy cancels with him. So finally we get then is that the energy then is equal to the inductance integral of the current integrated over the current from 0 to maximum current. Okay. What's the integral of IDI? I squared over 2. So this becomes equal to 1/2 the inductance times the current squared. This then is the energy which is stored within inside of the inductor. So the function, again, of putting an inductor typically inside of a circuit is to store energy for later use, just like a parallel plate capacitor, where in this case, the energy is stored within inside of the current, unlike the parallel plate capacitor, which is stored within inside of the charge. So remember, if I think about the parallel plate capacitor, the energy stored was 1/2 the capacitance times the charge squared. So this thing has identically the same structure as this guy. So yeah, the function of a capacitor was to store energy via the charge. The function then of an inductor is to store energy via current. Okay. So tomorrow, we'll then look at how do we actually solve self-inductance then? What is the inductance? It turns out inductance is very similar to capacitance, where it only depends on the geometry of the inductor. It doesn't depend on the current or the potential or any of that good stuff. Just like a capacitor only depended on the geometry of the capacitor, didn't depend on the charge and the potential and all that different stuff. So all that. So we'll do that, and then we'll have some fun sticking them in some circuits. So we'll look at 2 circuits. Hopefully we can get all that done in about 20, 25 minutes. We'll see how it goes. And then we'll do an exam, review for the exam. So it will be great. What's up? Go back to the what? This one? Yes. So yeah, so that's the back EMF, which is generated. Back EMF. What's up, Dylan? Go ahead, Dylan. Oh, the hygiene, yeah. So that's, yes. Oh, yeah, 1 item. Yeah. No, there's no limit to how minimum or how maximum. So whatever it is that you can get. Oh, the total grade and the grade. That's basically everything, but the way that's doing it is it's basically counting the extra credit against you. So if you were saying that your total points is let's say 300 out of 400, that 400 includes all of the extra credit possible points. So if you wanted to know your overall grade in that case, you would have to basically subtract off the extra credit. Because remember, the extra credit is just added on top of everything at the end. So basically, that 400 points, you'd have to figure out what that 400 points actually is. So that 400 points might be like, there you go. Yeah.
So it's not 40. Yes. So it should just be at 300.
Right, but then we also drop the low 60.
Yeah.
So you can also make it more complicated and subtract your low 60 and divide by 200.
I've already got my Excel spreadsheet.
Nice.
And it's
Sure.
Not about anything necessary.